In sections 3.4 and 3.5, we learned how to use first and second derivatives of a function to figure out where the graph would be increasing, decreasing, concave up, and concave down. It also allowed us to find points of inflection and find the critical points and figure out whether those might represent relative maxima or relative minima. In section 3.6, we're going to put it all together and use these tools as well as pre-cal tools to find out how to draw fairly accurate graphs of functions. Section 3.6 is going to be split over several videos, and this is the first. Something you should do before watching the videos is download and print a few copies of the function summary sheet. This is a great way of collecting together all the information that we're going to learn from the function as first and second derivatives. The information up at top captures information about the function itself. In the middle, first derivative information, and down here, all the second derivative information. So I suggest that you pause the video, print this out. It's on Blackboard under Exam 2 materials, other. So for our first example, let's see if we can complete a function summary sheet for the function x cubed plus 3x squared minus 24x. So to begin with, since this is a polynomial, we know that the domain is all real numbers. As for the range, let's leave that blank for a minute and come back to it. Now, since f is a polynomial, it doesn't have any asymptotes or holes. And for the x-intercepts and y-intercepts, we can find that just as we did back in pre-cal. For the x-intercepts, we set the function equal to 0. And we can solve this one by factoring. First of all, we can factor out an x. And then the trinomial is going to factor as x plus about 8 times 3, 6 times quadratic. This doesn't factor. So let's use quadratic formula for this part. For x, we'll have x equals 0. For this part, x will be negative 3 plus or minus the square root of 3 squared minus 4 times a times c, all over 2a. So that's negative 3 plus or minus the square root of 9 plus 96. So negative 3 plus or minus the square root of 105 over 2. So our x-intercepts will have 3 of them. One is 0, 0. One is negative 3 plus the square root of 105 over 2, comma 0. And the last one's going to be minus 3 minus the square root of 105 over 2, 0. And as you know, I like exact answers when possible. However, when we are going to go about graphing this, it'll be useful to have at least approximations for these numbers. And if you put them on the calculator, for the first one, you should get about 3.6. And for the second one, approximately negative 6.6. So 1, 2, 3 x-intercepts. For the y-intercept, we set x equal to 0, and that equals 0. So notice that 0, 0 is both a y-intercept and an x-intercept. Now what I'd suggest is that as you go along, you graph the information with the information you have so far. So here's the graph so far. We have x-intercepts at 0, 0, about 3.60, So let me count off. 1, 2, 3, 4. So an x-intercept here, roughly, and at negative 6.6. So negative 6.6 is somewhere around here. Now from the end behavior, we see that the leading coefficient is positive, which means the function rises on the right. And since the degree of the polynomial is odd, we know it'll have the opposite behavior on the left. So using just pre-cal information, we know that the graph looks something like this. And in pre-cal, we'd be perfectly happy with that as our result. Now in Cal 1, we're going to be able to refine this in a couple of ways. One is we're going to be able to use first derivative information to figure out where this local maximum is and where this local minimum is. But it'll also give us information about when the function is increasing, decreasing, and increasing again. And last of all, somewhere in here, we're going to have a point of inflection, since we can see the graph is concave down over here and concave up over here. In my picture, it looks like the point of inflection is about at 0, but I doubt that's accurate. So we'll have to work our way up to that. So that's our graph for now. Now let's look at first derivative information. Since the original function was x cubed plus 3x squared minus 24x, the first derivative is going to be 3x squared plus 6x minus 24. And let's go ahead and factor that down. Factoring out the common factor of 3, I have x squared plus 2x minus 8. And that'll factor as x plus 4 times x minus 2. So we can find our critical numbers by setting the first derivative equal to 0. So let's set that equal to 0. And notice that gives us two solutions, negative 4 and positive 2. Those are the critical numbers of the function. Now drawing a number line just for the first derivative, we can place our two critical numbers on there, negative 4 and positive 2. And I'll make a note that the derivative is 0 at each of those. And then just as we did a couple sections ago, we can test intervals to figure out where the function is increasing and where it's decreasing. This first interval extends from negative infinity to negative 4, the second interval from negative 4 to 2, and the third interval from 2 to infinity. And we can choose a number in each one of these and test it in the derivative. So for example, over here, I could choose x equals negative 5. In the middle, I'll choose x equals 0. That'll be easy to plug in. And over here on the right, maybe x equals 3. I can plug these numbers into any of the versions of the derivative, but we're going to find that using the factored version is going to be the easiest. For example, if I take f prime of negative 5, that's going to be 3 times negative 1 times negative 7, which is positive 21. So the derivative is positive on that first interval. On the second one, plugging in 0, I'll have 3 times 4 times negative 2, which is negative 24. So the derivative is negative there. And on the third interval, plugging in 3, the derivative equals 3 times 7 times 1. That's the product of three positive numbers, which is going to be positive. So when we're looking for increasing and decreasing, The function will be increasing any place its derivative is positive. So this function is increasing from negative infinity to negative 4, and also from 2 to infinity. And it's going to be decreasing in between. So it's decreasing from negative 4 to 2. We can also see that each of these critical numbers is also going to be a relative max or min. Notice that at negative 4, the derivative changes from positive to negative. So the function is increasing and then decreasing. So that's going to be a relative max. So we have a relative max at the point negative 4, comma, f of negative 4. And notice that over here at 2, the derivative changes from negative to positive. So that's going to be the location of a relative min. So the relative minimum is going to happen at 2, comma, f of 2. Now remember, technically, the maximum and minimum are the y-coordinates of these points. So let's plug back into the original function to find out what those y-coordinates are. If I plug negative 4 back into the original function, I have negative 4 cubed plus 3 times negative 4 squared minus 24 times negative 4. And I get 80 for that. So the relative maximum is at negative 4, comma, 80. And for the relative minimum, I plug 2 into this function. And when I do that, I get negative 28 as a result. So the relative minimum happens at 2, negative 28. Now, when we were identifying these relative extrema, we were saying in words that there's a relative maximum of 80 at negative 4 and a relative minimum of negative 28 at 2. On the function summary sheet, it's going to be okay for you simply to list the ordered pairs. So if you're keeping track, then what we filled out so far is this top section, except for the range, and we filled out this middle section. Let's see how we can translate this information into the graph. We know that the relative max is going to happen at negative 480. So here at negative 4, that's where our maximum should happen. So let's maybe make it a little bit steeper. Let's say that this is a height of 80. So here's that maximum point, negative 480. And the minimum is going to happen at 2, negative 28. So that minimum will fall just in the right place. This minimum is at 2, negative 28. So far, so good. Finally, let's look at the second derivative and see what that tells us. The first derivative was 3x squared plus 6x minus 24. Taking another derivative, we get 6x plus 6. And let's set that equal to 0. That, of course, gives us negative 1 as a solution. So now let's draw a number line for the second derivative. The only point of interest is x equals negative 1. And at that point, the second derivative equals 0. So I'll indicate that by putting a 0 on the number line. The negative 1 breaks the interval up into 2 pieces, the number line into 2 pieces, from negative infinity to negative 1, and from negative 1 to infinity. And we can test the point from each one of those intervals in the second derivative. So in this first interval, maybe I can choose x equals -2. And in the second interval, maybe x equals 0. Let's plug each of those into the second derivative. F double prime of -2 is equal to -12 plus 6, which is -6. So the second derivative is negative on the first interval. In the second interval, plugging in 0, f double prime of 0 is +6. So the second derivative is positive over there. So let's see what that tells us. The graph is going to be concave up any place where the second derivative is positive, and the second derivative is positive on the interval from -1 to infinity, and concave down any place the second derivative is negative. Now there are possible points of inflection anytime the second derivative is 0 or undefined. Here the second derivative is 0 at -1, and notice that the concavity does change there. It changes from concave down to concave up. So that means that there's indeed going to be a point of inflection at -1. And the last thing we need to do here is figure out what f of -1 is to get the y-coordinate at that point of inflection. Remember, to get the y-coordinate, you have to go all the way back to the original function. So that'll be -1 cubed plus 3 times -1 squared minus 24 times -1, which is -1 plus 3 plus 24, or 26. So the point of inflection is at -1, 26. And maybe we can just indicate that on the graph this way. At -1, +26. I'll just write POI for point of inflection. And notice that the graph is consistent with it being concave up from -1 to infinity, and concave down from -infinity to -1.